Thank you, Chairman, for the introduction. The title of my talk is Parameter Identification Strategy for Online Detection of Faults in Smart Structures. This is a joint work with Pasquale Montegiglio from Technical University of Bari and Adnan Kefal from Sabanci University. System identification techniques can be classified into main categories, parametric and non-parametric methods, where with non-parametric we mean the system model structure is unknown. With parametric methods we mean the system model structure is well known. Another difference is between frequency domain and time domain methods. In this contribution, a novel parameter identification approach for both real-time or offline detection of faults in smart structure is proposed, and it is applied to piezoelectric systems for energy harvesting and or sensing. The application will be mainly focused on three classes of electromechanical devices: the linear time invariant system, the linear time invariant system, and the nonlinear system. The starting point of our problem are the governing equation for a linear piezoelectric solids, where the electric enthalpy can be used to determine the constitutive relations of the problems by deriving the electric enthalpy H with respect to the strain tensor epsilon. It's possible to obtain the stress tensor, while by deriving the electric enthalpy H with respect to the electric field E, it's possible to obtain the electric displacement D. Standard boundary conditions of Dirichlet and Neumann types are used, and the overall problems is governed by a set of 4 partial differential equations. So the PD problem, where the 3 displacement components and the electrical potential are the unknowns, U and phi. The finite element method can be used to reduce the PDA problem into a set of ordinary differential equations, or the E, where with N we are indicating the shape functions, and with A we are indicating the nodal values of the displacement U and the electric potential phi. According to standard finite element procedures, the matrices can be assembled just adding the element contribution and the Gauss point contributions. The overall procedure is implemented using the tools available by SFEM and SCHEN, mathematical finite elements codes. So, however, we need to derive a state space model starting from our finite element model, because the differential equations of motion symmetric forms have these expressions where with M, U we are indicating the mass matrix, with C we are indicating the damping matrix, and K represents the stiffness matrix, while KU it represents the coupling stiffness matrix term. The mechanical Neumann boundary conditions are given by the terms F, that is a function of the ground motion U for the energy harvesting structures that we will consider in the examples. So a coordinate transformation is used for the mechanical and electrical degrees of freedom, such as it's possible to project in the modal space the differential equations. After the introduction of a modal participation vector tilde, and the solution of the eigenproblem to determine the frequencies omega r, it's possible to define a modal mass, modal damping, modal stiffness, and modal piezoelectric matrices with terms M tilde, C tilde, K tilde, and theta tilde. The same projection is required for the electrical equations. So the resulting equations are given in the red rectangles. You can see that the model order reductions is achieved since the resulting finite element equations are projected in the modal space. With R tilde and C tilde, CP tilde, we are indicating the modal resistance and the capacitance matrices in the modal space. Another steps is to rewrite the ordinary differential equations obtained through the model order reductions in the state space form, where with eta we are indicating the mechanicals, dynamic unknowns of the problem, and with V we are indicating the voltage at the electrodes of the device. With gamma, after introduction of gamma, lambda, theta, and F tilde, we can express the problem as a function of a matrix A that collects the unknown parameters of the that are required to describe the device response. So a classical state variable forms is finally achieved, and in these slides the numerical implementation is briefly discussed. The unknown parameters vector is given by lambda. An identification error vector is introduced through the difference between the system response y vectors and the measured values experimentally of the system response. Then, since we want to use Lyapunov theory to derive the parameter identification algorithm, we introduce an energy function that contains the sum of the errors, so EI, and it is quadratic form. And furthermore, we define the evolution of we force the evolution of the vector of unknown parameters to follow this expression. It means it follows, it is given by the product of a gain matrix K times the directional derivatives of the energy function psi with respect to the unknown vector of parameters lambda. So forcing this evolution for lambda dot, it is possible to derive the expression of psi dot. And you can see that the expression of psi dot is again a quadratic form, and therefore an exponential asymptotic convergence to equilibrium points for the artificial dynamic systems is guaranteed, since both the conditions of the Lyapunov theories are satisfied. Non-negatives psi dot and positives psi. The condition of psi dot requires the computation of the directional derivatives of the error E vector with respect to lambda, that is a function of the directional derivatives of the system response vector Z with respect to lambda. To compute these sensitivities, we have to solve another dynamic problems that can be expressed again in the state space form as a function of Q dot and Q. This is the overall algorithm in block diagrams, where you can see that the sensitivity of the parameters, the sensitivity of the system response with respect to the unknown parameters works as a feedback on the parameter identification algorithms. So this is a summary of the state space equations that are required to be solved at each time steps of the process. So the input force, it's given, the input by the ground motion UG, that it's the input for both the real system and its system model. So then the real systems that we want to identify, it provides as output a vector Y experimental, that is a function of t. While the system model will provide an output Y out, that is a function not only of time, but also of the lambda that are changing during the procedures. So the aim, it is to reduce this difference between the expected output of the system response with respect to the experimental results. So what it will happen, it is that a steady state conditions is achieved based on the satisfactions of the Lyapunov theorem's conditions, such as the asymptotic values of lambda will provide the unknown set of parameters. It means that lambda star at the time goes to infinite will reach the unknown set lambda, such as the error that is a function at each time instant of lambda star will go to 0. This is the first benchmark problems. We have just considered linear time invariant systems, piezoelectric structures and energy harvesters that is forced by the ground, and the unknowns are the output at the electrodes and the tip displacement in the modal space. So you can see that the parameter K1, that is the stiffness of the beam, it evolves. It's one of the unknown parameters. It evolves until to reach an asymptotic value. That is the final values we want to identify. The same it is for the decoupling term E1. And in this picture, you can see the evolution of the errors between the estimated, between the output of the system response, Y1, with respect to the experimental YREF results. So both the errors goes to zero. It means the parameters are identified correctly. And this is the synchronizations between the system response and the experimental result. You can see that the system response will adapt its parameters to catch the experimental results. The procedure is stable also in presence of noise on the linear reference system output, since it has a filtering capabilities. You can see that even in presence of an error on white noise error on the output of the system, it is possible to identify the parameter K1 and the parameter E1 correctly. You can see the noise affected reference in orange, the reference system output, it means the experimental values in this case, in green. Again, the model output that can catch, can synchronize with the reference system output, both for the tip displacement and the voltage at the electrodes. The procedure is stable also in presence of randomly time-varying stiffness coefficients. Again, there is a filtering capabilities. You can see the parameter we consider a K stiffness of the real systems with affected by noise, and the reference value that is given by the mean, it's the green lines. And again, the systems can identify the parameters, the blue curves, very effectively after 0.5 seconds. Again, you can see in the picture as the electric parameter E1 is identified correctly, as well as the stiffness value. And this is the synchronization for this case between the model response and the reference system response. The reference system is representing an ideal experimental value set problems. So going to the main scope of this paper, this procedure can be used for fault detection, because when we have faults in the structure, a softening in the dynamic response can be captured by these procedures. You can see we made in ideal systems, experimental systems, where the stiffness parameter is changing after 5 and 10 seconds. Again, the parameter identification strategy can estimate correctly these variations in the stiffness that represents, as we told, the presence of a fault in the structures. And this is the synchronization between the adaptive model and the reference system's response. For the case of softening, dynamic response, or sometimes also it's more uncommon, but stiffening in the dynamic response can appear due to faults appearance. And again, we have considered a changing K1 parameter stiffness. And again, the systems can capture and synchronize the model systems, the experimental results very efficiently. Finally, this is instead nonlinear systems due to faults in the structure that is presenting a Duffing type nonlinearities. And again, we are demonstrating that the parameter identification procedure is able to capture after 5 seconds the new value of stiffness after a fault is appeared. So these are the conclusions. A new algorithm for real-time detection of faults in the framework of electromechanical devices employed for energy harvesting sensing application is proposed. The computational strategy is based on a sensitivity feedback analysis. The identification problem is formalized by a proper set of dynamic ordinary differential equations, which equilibrium point correspond to the problem solutions. The proposed computational strategy does not fail even when traditional iterative algorithms based on Newton-Raphson do not converge due to highly non-linearities. Those are some references. Thank you for your attention.